Hello and welcome back to Manifolds, the video series where we talk about generalized surfaces and the integration we can do on them. And in today's part 56, we will look at a special case of the generalized Stokes theorem. And this one is quite famous because it's the classical integral theorem of Gauss. This one you might also know as the divergence theorem because it connects an integral over the divergence of a vector field to an integral over a boundary of a manifold. However, as always, before I explain more details, I first want to thank all the nice people who support the channel on Steady, here on YouTube or via other means. And you might already know that you can use the link in the description to download the additional material for the videos. For example, you can download the PDF versions for the videos, which might be really helpful if you just want to get an overview over the former videos. And now for the beginning of this video, I want to start discussing Stokes' theorem in Rn. This means we consider a submanifold M embedded in Rn. More precisely, the dimension of the manifold should be maximal, so we have an n-dimensional manifold. And as you know, Stokes' theorem allows that we have a manifold with boundary, so the boundary is an n-1 dimensional manifold. And moreover, Stokes' theorem also requires something you should not forget, namely that the manifold has to be compact. So for example, in the three-dimensional space, this is quite easy to visualize. There you would say you have a full body as a three-dimensional object, which has a two-dimensional surface. In other words, this is the boundary of the manifold that we call del M. So in general, the boundary is n-1 dimensional, so just a hypersurface in Rn. So you could say that we have very concrete Riemannian manifolds here. Therefore, we know from former videos that we have a continuous unit normal vector field. This one is defined on del M, and we can choose it as outward pointing. For this you can just check part 37 and 47. And the common notation we have for that is just a capital N. And to visualize that in the picture here, you can just put a normal vector to each point on the boundary. This is quite important because these normal vectors are used in Gauss's theorem. Indeed, because this outward pointing unit normal vector field is uniquely given, we can use it to simplify Stokes' theorem. So this means we don't get something new here, but a simpler formulation which could be really useful in applications. And here please note, I formulate everything in Rn, but Gauss's integral theorem could also be formulated in a more abstract way. Okay, then let's start with the requirements. We want that M is an n-dimensional submanifold of Rn, which is compact and of dimension n. So please recall, compactness is crucial in Stokes' theorem, so we have it either in the manifold or in the volume form we integrate. In fact, now in Gauss's integral theorem, we will not focus on a volume form, but rather on a vector field on the manifold. Hence, here we just have a differentiable map we call V. This means on each point on the manifold M, we put an n-dimensional vector. So it's just a classical vector field from Rn into Rn, and there we know it has a well-defined divergence. And this divergence is a nice scalar function we can just integrate over the whole manifold. In that sense, we just have an ordinary n-dimensional volume integral. So you see, this integral is already understandable without knowing much about manifolds. However, now what we get here in Gauss's integral theorem is that this integral is equal to an integral over the boundary of M. And in fact, the differential form we integrate here on the right hand side is just the canonical volume form of the boundary. But obviously this is not all, because it also gets a coefficient in front. And there we simply combine V and N in the standard inner product of Rn. And usually we would use pointed brackets to denote this inner product, but in order to keep the formula short, I just use a dot in between. Indeed, this is not so uncommon, so definitely something we can do here. So there we have it. This is the whole formulation of the important divergence theorem in Rn. And for the sake of completeness, let's also write down the explicit definition of the divergence of a vector field V. It's quite simple. You start with the first component of V and use the partial derivative, namely the partial derivative with respect to the first component. And then you do the same with the second component and the second variable. And then this continues, and the important thing is that you just add up all these partial derivatives. And that's it. This is the whole definition of the divergence of a vector field on Rn. However, at this point I can already tell you that this concept of a divergence of a vector field can also be generalized to abstract manifolds. But this is definitely something we should discuss in a separate video. In this video we still concentrate on the most important application of Gauss's integral theorem, namely in Rn. And now let's simply put together what we know to formulate a proof. And there the idea is quite simple. We put some stuff together and then we finally apply Stokes' theorem. And maybe the first thing I should remind you of is the canonical volume form of Rn. It's the standard determinant, and you can formulate it by using our coordinates x1 to xn. So it's a wedge product with n factors. Clearly this is the n form we integrate here on the left hand side, and we integrate an n-1 form on the right hand side. In fact, the canonical volume form of the boundary manifold can be constructed by using this n form. This is also something we have discussed in part 37 already. It's actually quite simple because we just fix one component by using the unit normal vector. And the common way to denote that is to use such a lying L. And on the right of that we have an n form, which implies that the result is an n-1 form. In fact, in Rn the whole thing is quite simple because we just have the determinant where the first column is now given by the unit normal vector. And then the other columns can still be used as inputs for the tangent vectors. So this is quite important because it tells us how we can connect both volume forms here. Moreover, we can do a similar thing with the divergence of V. This means we can get the divergence of V by using V in the volume form of M in a similar way. So let's simply put V into the volume form of M. Indeed, here we don't really have to distinguish between Rn and M if we agree that we only work in M anyway. Obviously, inside the set M there is no difference at all. Therefore also here we just get the determinant where the first column is given by our vector V. However, please don't forget it's a whole vector field, so we would calculate this determinant for each point of the manifold M. And then you see what we could do is to use the Laplace expansion for the first column. This means we could expand the determinant along the first column to get a whole sum of determinants. But in that case, the resulting determinants are one dimension lower. So for example, in the first step we just have V1 and then the determinant is given where the first row is cancelled. This means we could describe that with the wedge product here where dx1 is missing. And then in the next step we would have V2 multiplied with the determinant where the second row is cancelled. Hence there dx1 is there, but dx2 is missing. And moreover, you also know that we have a minus sign included. And now you should see it's not hard at all to make this into a general formula where we have Vi. There we just have to say that the dxi component is missing in our wedge product. And indeed we have a common notation for that. We just put a hat on this component. So the hat just means that this component is actually not included in the wedge product. And moreover, we should also not forget about the alternating sign change we have here. In fact, we can just write it as -1 to the power I plus 1. And there we have it. This is the formula we get for the n-1 form here. Which means if we want to find an n form, we can apply our Cartan derivative for this n-1 form. Hence we just write d of v into omega m. And this means that we just apply our d operation to the whole sum on the right hand side. And there we can just use all the calculation rules we know. For example, we have the linearity, so we just have to put d to the component vi. Or to say it more precisely, we just have to calculate the Cartan derivative of this n-1 form, and then we sum them all up. And the calculation here is not complicated at all, because we can use the general sum formula we have, but we already see that only one partial derivative of vi remains. Namely, it has to be the one with respect to the xi component. Simply because dxi is the only one form missing in our wedge product here. So in the end, what we have here is the wedge product of the one form with all the other ones here, so we already have our n form. But obviously you also immediately see that we can push dxi to its correct position. So we need some exchanges here, and these give us a sign that directly cancels with the sign in the front. Hence what remains here is just the sum with plus signs. So this is a nice result, which immediately can be simplified even more, because as you can see, here we have the divergence of the vector field and here the volume form of Rn. So in other words, it's just the canonical volume form with the divergence as a coefficient in front. And indeed this is quite helpful, because it's exactly the function we want to integrate in Gauss's integral formula. This means we can already simplify the volume integral in the formula. So please note, this n-dimensional integral we have is exactly our integral over this volume form. And exactly there we can use our result from before, where we have the exterior derivative included. And at this point you should realize that we can use our generalized Stokes theorem. Which means now we can go to an integral over the boundary of M. And indeed Stokes' theorem is easy to remember, we just have to integrate this n-1 form. However, the mathematically exact statement would say that we have to push it to the boundary. And as always, this is done by the pullback of the inclusion map I. Therefore, to finish the whole proof, we just have to check what this n-1 form on the boundary actually is. And the best way to do this is just to look at an orthogonal decomposition of our vector field V. And by that I just mean that we split up V into two components. This is a standard thing we can always do when we have a complete inner product space. So in this case here we have our manifold M, but we are only interested in the boundary anyway. So at a given point here at the boundary, the vector V might go like that. And therefore we directly get the decomposition of V into two orthogonal components. One part goes into the direction of n and the other one is orthogonal to it. So let's say we have V with index n and V with index t, where Vn lies in the one-dimensional subspace given by n, and on the other hand Vt is a tangent vector at the boundary. Now this splitting is important because, as we will see, only the part that goes into the direction of the normal vector is important for the whole integration. And in fact, this part can be just written as an orthogonal projection of V onto n. In other words, here we just have the inner product V with n, and this is the coefficient for the vector n. So please note, this formula for the orthogonal projection works because n is a unit vector. And now let's use this decomposition to calculate the n-1 form we want to integrate. And indeed, because of the linearity of the operations, we have the splitting there as well. So in the first part we have Vn, and in the second part Vt. But obviously here inside we can use the same calculation as before, which means what we get is just the determinant. And there in the first column, as we know, we find our Vt. And now the thing is that Vt is already a tangent vector, and all the other columns also have to be filled in by tangent vectors. And since our tangent space is only n-1 dimensional, we know that these vectors are always linearly dependent. So no matter which tangent vectors we put in, this determinant will always give us 0 as a result. Hence we only have to consider the first part here, and there we already know that we can put in our formula for the orthogonal projection. So we can just pull out the coefficient, and inside we just find our normal vector n. And this result is quite interesting because we have discussed it before. It's exactly the canonical unit form of the boundary. And with that we are done, because now you see in the formula above we have exactly what we wanted. And with that, Gauss's integral formula is proven. So you see, the whole thing was not so complicated because we just had to rewrite some volume forms, use Stokes' theorem and this decomposition of V. And with that we have the justification to say that Gauss's integral theorem is just a special case of the general Stokes theorem. And indeed, in order to see the advantages of this divergence theorem, I would say we should look at some examples. So let's do that in the next video, and let's meet there again. Have a nice day and bye bye.